For centrifugal pump, some good things are there. Centrifugal. Okay, so positive displacement pump or reciprocating pump, there are some good things, because this can give very high amount of pressure, which normally it will be required for your gas lifting application. But centrifugal pump will have some benefit is there. Flow rate is high, one thing, flow rate is high. Pressure will be high if you can create multiple staging. So multiple staging creates high pressure. Okay, maintenance low. Why maintenance low? Because it is having very limited moving element. When you are designing an engineering system, you have to consider that if you have many moving element, the system life will be lower. Okay, in centrifugal pumping system, what you have, you have motor, shaft connected to your impeller. Okay, so only one shaft is rotating, impeller rotating, your motor system rotating, and there is no other moving element. But in the reciprocating pumping system, valves are continuously moving. Like in pumping system we discussed, like several valves are there. So valves will be opening, closing continuously in back and forth motion. Several motions are there. So that will reduce the system life. But in this case, there is no such thing, no valving system, only one shaft rotating continuously. So maintenance is low. Okay, no cooling water. Okay, because a very high volume flow rate and compression ratio also not very high, so cooling water not so much effective. Okay, continuous flow. Okay, in reciprocating system it is not continuous flow, the pulse are going, right? So pulse are going, that means you need some accumulator, or your system will get some continuous stress. Okay, alternating stress, so that will be harming actually. And high capacity, flow rate is high. Okay, so these are positive thing. But reciprocating system, positive thing is that basically it is a very high pressure ratio it can give, and you can get very high volume flow rate. You can create multiple staging or multiple compressor pistons if you are using, like say duplex or triplex type, or quintuplex, many other type you can create, and you can get more flow rate in that case. Okay, for formulation for calculation different parameter for centrifugal pump. Centrifugal compressor. Okay, PV per N equals constant. We are assuming polytropic process. So N denotes the polytropic exponent. Okay, and if I have K, the specific heat constant, so, or specific heat ratio, then N and K related like this: N minus 1 by N equals K minus 1 by K into 1 by eta P, or EP they are writing. So eta P is polytropic efficiency. Okay, it is polytropic efficiency. So EP formula is given 0.61 plus 0.03 log of Q1, inlet flow rate. Okay, Q1 is inlet flow rate, and unit is CFM, cubic. And compression ratio, R equals P2 by P1. Okay, and Q1 becomes PB by P1 into T1 by TB into Q. Okay, where Q under standard condition, Q under standard condition and inlet condition Q1 inlet condition. For example, if certain gas is given at your standard condition, let's say 1000 mmSCF, but inlet condition maybe pressure will be, temperature will be different, so the gas volume will change. So you have to convert in this way, okay, using this formula. T1 P1 inlet condition and PB TB is your standard condition. Okay. Now RP, polytropic ratio, N minus 1 by N okay, into K minus 1 by K 1 by eta P or EP whatever they write, okay. Now T2 equals T1 RP, okay, polytropic ratio, this is polytropic ratio. Okay, R power capital RP, and Q1 can be calculated using Z1 PB T1 Z2 P1 TB Q, okay. So if Z1 Z2 changing, then you have to repeat the formulation. If normally I give Z1 Z2 value, let's say equal value, so in that case you don't have to move again, reiterate again, okay, for simplification. See the problem here. Gas specific gravity is given 0.68, specific heat ratio is given, or K value is given, gas flow rate Q is given, inlet pressure is given P1, inlet temperature is given 100. So this is inlet temperature T1, that means you have to convert T1 plus 460 Rankine, okay. Discharge pressure also given, polytropic efficiency EP or eta P, whatever you write, is given, and Z I am given same value, so that you don't have to reiterate again. And how this problem to solve, okay. First calculate R equals 600 by 250 given, right, so it is coming 2.4. Now Q equals 144,23333, okay, 24 into 60 1 SCFM, okay, because you are MMSCF you are converting now, so you got SCFM. Now Q1 equals, you are getting PBT1 PBTB T1 P1 into Q, okay. So from there you will write 14.7 standard condition into 250 is given P1 and 560 temperature and 520 temperature, okay. So 5 this is 100 plus 460 equals 560, and another temperature is given, okay, standard condition. So standard condition means temperature equals 60 plus 460 equals 520 degree Rankine, okay. So TB is there, so we got 520. So finally this is coming to be 6332 CFM, okay. Now EP or eta P, whatever you write, 0.61 plus 0.03 log of 6332 equals 0.724. Now you calculate RP, polytropic ratio, N minus 1 by N equals 1.24 minus 1 1.24 this will give into 1 by 0.724 equals 0.2673. So T2 is coming 560 into 2.4, 0.2673 equals 707.7 degree R equals 247.7 degree Fahrenheit. Okay. Now the gas capacity. Gas capacity Q1 equals 0.97 0.97 into 14.7 into 560. Okay, it's not, it should not be 0.97, it should be Z by Z into 250 into 520 into 1000. Okay, so it will be like 8000 CFM. Okay, so this, up to this you calculate, but if you go further there will be lots of iterations. We are not going for the iteration. Okay, now you can put HP, you can calculate HP value. So I am leaving to you to calculate. Okay, so formula is given in the book, you can go through the book also. There are other type of compressor, rotary compressor. Rotary compressor, it can be like gear type, it could be scroll type. Like in refrigeration system you have one, like say one pipe and one stylus will be rotating. Okay, it will be compressing the, squeezing the pipe. Okay, it will take fluid from here, squeezing the pipe, you are delivering. So this type of compressor is there, or progressive screw pump type of compressor also possible. So there will be different types of rotary compressors. So normally we do not use all this many types of compressors. The centrifugal and reciprocating are more common type of compressor. Centri and reci. Reciprocating type and centrifugal type, most common type. Common type used for gas lift application. Okay, and if you want to go for further study, then I have given one link, you can go through that. Reciprocating compressor, you have already seen this. Reciprocating pump, same principle, it will work like this. Okay, so one piston is there, piston will be moving forward, backward, and there will be valve V1, V2. So V1 and V2 will be working alternatively, and that will give you pressure development. Let's say you are sucking gas or air and you are delivering here, okay, to a certain volume and into a certain chamber where you are storing the pumped gas or air. Okay, so that is the basic principle of reciprocating compressor. Whenever you are discussing about reciprocating compressor, first you have to understand the indicator diagram. How this indicator diagram look like? Let's say we have one piston cylinder arrangement. We have one piston cylinder arrangement as I have drawn for your pump in previous lecture. Okay, and I have PV diagram, volume and pressure diagram, and this is TDC, this is BDC. Okay, and valve is there, V1, V2, and when, let's say my system is completely filled with air, now start compressing. Okay, start compressing, and after certain compression it will be starting delivering. Okay, why after certain compression? Let's say you are having one cycle pumper, that roadside cycle shops will be there, they will have simple pumper. Your cycle air is tube air is not sufficient, pressure is not sufficient, so you go there and you pump yourself, right? So if when you are pumping, after you try to compress it, after certain compression only the air will enter into a tubing. when you are pressurizing from the top, at beginning when you are pressurizing, so that time air is not entering. After certain compression, air will be entering. What is happening? Because tire is having certain pressure, and your pumper, okay, your pumper is having certain pressure, pumper or cylinder or piston cylinder arrangement. Now when piston cylinder arrangement, this piston cavity or inside the it will create pressure higher than the tubing pressure, then air will enter. Okay, let's say 2 bar pressure is there already in my tube, and when you are pressurizing, you must pressure more than 2 bar, then air will enter into tubing. Okay, so what will happen when you are pressurizing 1 bar to 2 bar? So there will be lots of compression, air will be compressing, then it will enter into tubing. Okay, so that is happening. Initially you take air, it will start compressing, then based on your delivery requirement, okay, if tube pressure is very high, then your compression also will be very high. Okay, so here you see the figure I have drawn, 1 to 2 initial compression happening, then when you reach to pressure required in a chamber or a tubing or tube, cycle tube or motorcycle tube or truck tube maybe, so then your fluid will be getting, or air will be getting, or nitrogen or natural gas will be getting delivered. Okay, so first compression happening, then delivery happening. Okay, so piston initially at bottom dead center, then it will be moved towards top dead center. Before top dead center, it will be delivering air. Okay, then when delivery is completed, then again you try to move back. Okay, 3 to 4 it will happen, then 4 to 1. Okay, here then process is like this, 1 to 2, piston moving from BDC to TDC. Okay, and it is polytropic compression normally. Polytropic compression. Okay, so PV per N equals constant. Okay, or it is not completely adiabatic, not completely isothermal, so in between something. Now when it is reaching to 2, after that 2 to 3, air delivery, air or natural gas delivery, DELIVERY. Okay, 2 to 3 delivery is happening at constant pressure, Okay, when piston moving from BDC to TDC, pressure increasing. When it reaches 2, after that you are delivering pressure at constant pressure, or isobaric process actually 2 to 3. Then 3 to 4, piston just turning, so there is no process happening, actually pressure is going down. Okay, so piston turning, only turning towards opposite direction. Okay, and 4 to 1, what is happening? Piston is taking air filled in the cylinder. Okay, so I am assuming there is no clearance. I will explain later. Okay, now this is the simple piston cylinder arrangement, how the pressure is getting developed. Now in practical situation, there will be one clearance between TDC and piston. Piston maximum distance cannot touch the TDC, top dead center. Okay, cylinder is here, let's say this is my cylinder, Okay, so piston moving, it will not touch the end. Okay, so what will happen in that case? In that case, PV diagram, and I have again piston cylinder. Okay, TDC, and this is BDC. Piston will be moving. Okay, And okay, so what happens, initially you have piston at 1, piston cylinder is filled and you started compressing. Okay, after compression you are delivering 2, 3. Now 3 is not touching the y-axis. Okay, this is y-axis, you are not touching the y-axis. Okay, why? Because piston should maintain certain small amount of gap inside the cylinder. So there's because of mechanical reason, piston cannot hit the top dead center. Okay, in a sucker pump also, actually you gave some gap. Okay, that was creating your gas lock issue, you can remember. Okay, so here you create certain gap, so that is called clearance volume. Okay, this area is clearance volume, piston cannot reach here. Okay, clearance volume, clearance volume. Okay, this is in PV diagram we can VC, clearance volume, and the piston moving the distance. Okay, so this is called VS. VS is called swept volume, swept. Okay, this is called clearance volume. Okay. So piston will be moving from 1 to 3, actually location 3 is maximum piston can travel, and 3 to certain gap is there. Okay, this gap piston cannot travel, so this gap will be filled with air or whatever compression gas you are using. If you are compressing air, then air will be filled. If you are using natural gas, this gap will be filled with natural gas. Okay, so what will happen then? After 2, piston moves from 1 to 2, then 2 to 3, then 3 to 4. Where is 4? 4 will be here. No, sorry, 4 will not be here, 4 will be here. I'll draw some different figure. Okay, 4, and it will be connected like this. Why 4 is curved now? Previously I have drawn 3 to 4 vertical line, 4 to 1 horizontal line. Now I am not doing that. I am drawing 3 to 4 as a curve. Again, this is PV power n equals constant. Actually, this is also polytropic process. When piston moving up and down, we can assume adiabatic also, there is no issue. Okay, so small air will be there inside the cylinder. Okay, and you compressed, you have one cylinder. Okay, you have one cylinder. Okay, now you compress, you compress up to this, some small amount of gap is there. Okay, so this, when piston is at this point, the pressure in this gap is very high. Okay, when piston will try to move backward, so this pressure will be expanding. Okay, after certain expansion, only fluid intake will be happening from outside. Okay, so you see 3 to 4, actually pressure, whatever inside air, remaining air was there, so that was expanding. Once it reaches to 4, it becomes normal pressure. Normal pressure is outside or intake pressure, then fluid will enter into the cylinder. Again 1 to 2 we are delivering that fluid, 2 to 3 again 1 to 2 compressing, 2 to 3 delivering, 3 to 4 again this clearance gap, that much of air will be expanding up to 4, then your intake happening. So what is the difference now? This is no clearance volume, no clearance volume. Okay, there with clearance volume, clearance volume. Okay, this is the left side and right side picture, no clearance volume with clearance volume. Now the sequence similar, only the intake part length is reduced. Okay, so you see 1 to 4 both cases, and left case V1 minus V4 more than V1 minus V4 right case. How should I write? Okay, I should write like this, right okay, this is left case means this one, right case means this one. This one I'll draw like this. This one is right case. Okay. So if no clearance volume is there, your total volume intake from outside is higher, so total mass pumping or compressing is more. But if you have clearance, then it is a problem. So your intention should be reduce clearance as much as possible, so that V1 minus V4 will be increasing and you can reach to the left side figure. Okay, but practically not possible, but you can try. And you can, if you can create isothermal compression, okay, so that will be very good. But isothermal means you need very long time, so you don't have that much of time, right? So you can create polytropic process. Swept volume definition. Swept volume is equals V1 minus V3. Okay, and mechanical efficiency. Mechanical efficiency equals air indicated power, air indicated power divided by shaft brake power. What is shaft brake power? Shaft brake power means your piston cylinder moving and your motor running, so shaft is rotating. So shaft is transferring power to your indicated power or machine, so there will be lots of losses. Okay, so shaft is giving more power, but actually indicated diagram whatever power it is showing, it is lower. Okay, so shaft power is lower, so lower power divided by higher power, that is your mechanical efficiency. Okay, volumetric efficiency. Volumetric efficiency equals volume of free air delivery FAD per stroke divided by swept volume per stroke. Okay, what is free air delivery? Free air delivery means after delivery you are assuming the air is delivered at the atmospheric condition. So pressure and temperature, if you change the pressure, what will be the volume actually, so that volume you can take. Okay.